Yeah, please go ahead with the second half.
Thank you so much. So now we're getting down to defining the chromatic symmetric function. I don't know if there's a good way for me to pronounce it. Chromatic versus chromatic. I have no idea. That sounds terrible. Let's not do that. All right. So K-theoretic analogues of objects throughout algebraic combinatorics are often take a form as a multiple valued superposition. And in the particular case of these Grothendieck functions, one could view them as taking the Schur functions and allowing multiple values within boxes of a tableau. So our idea is we're going to apply this to the chromatic symmetric function, and instead of coloring a vertex with a single color, we're going to give it a set of colors. So this is what we're going to do, and we're going to continue using this bar notation. X bar G is, in this case, we're going to sum over all ways to color the vertices of the graph properly still, in the sense that adjacent vertices still cannot have a color in common, but each one can now get any non-empty set of positive integers as a color. And we still do the same thing. We take a product over all vertices and we just give it one exabyte for each color that is used in I.
Does not having the same color mean it doesn't intersect, or
yes,
not equal?
It means that the sets do not intersect. There's something to be considered about whether they're not equal or have a certain size of intersection, but for our purposes, we went for have no intersection, which is equivalent to, for example, replacing each vertex with a clique of some size and coloring that clique, where you keep all of the adjacencies the same. In our case, we are, however, allowing simultaneously any replacement of the vertices by any size clique, and we sum over all of these possibilities. One could view it that way as well. So as an example here, let's go back to a graph delta, but now I'm adding a yellow color that is 4, so that this is easier to do because this graph is very hard to use multiple colors with just 3. And here, for example, now this vertex has received 2 colors, yellow and blue, and it took me a while to figure out how to draw that in this graphic. And this one receives 2 colors, green and blue. That's 1 and 2. And so here we have 3 instances of blue, one here, and one here. So that's an x1 cubed. 2 instances of green, that's x2 squared, an x3 and an x4. Over here is a different one. Here we have one vertex that's multicolored. It's contributing the x3 and the x4. And the x1 squared, x2 squared comes from other vertices receiving 1 color. So some things to notice here. First of all, that this function is, of course, not homogeneous. It consists of terms that have degree equal to at least the number of vertices of the graph, but in general might have arbitrarily many more. So this is going to be still an infinite sum of terms, but now it's not a homogeneous one. And in general, one could also weight the vertices as before and do the exact same thing. If we have a vertex with a weight, then each of the colors for that vertex receives the weight bonus. So in this context, for example, if we have these weights, we're going to have 6 total blues, 3 here, 2 here, 1 here. So we get an x1 to the 6th. We get an x2 squared from, let's see, not that one, that's this and this. We get an x3 from here, and we get an x4 squared from here. So just the same thing, we allow vertex weights, and we can make this go. And so first question, and there's a pretty natural choice here for an M basis, K-theoretic M basis here, which is that we could define that, say, M3221 is just the K-chromatic symmetric function of the complete graph of type 3221. This ends up making a lot of sense because under this definition, we do have a nice natural generalization of this expansion to the M basis. Namely, we get one M tilde bar lambda of C for every C that is a cover of G by stable sets, and lambda is the integer partition of the weights. So previously, if we had done vertex-weighted graphs and looked at their M basis, this would have been a sum over all partitions of the graph into stable sets, and lambda would be lambda of pi. Here, we allow more things because C now just needs to be a cover, meaning that the stable sets we use need not be disjoint, because, well, that's because vertices can receive the same color, but it's still the case that each color applies to a stable set. So we're throwing these stable sets on here. And here's a graphic that Sophie has contributed. So for example, here, and these should have bars over them, but that's okay. And that was unfortunate, but we'll deal with it. So here there are these distinct stable sets. So first of all, each vertex itself is a stable set, and also corresponding to green, blue, and purple. And we also have the red stable set, which is the only non-trivial one containing two vertices. And what is this expansion into the K-chromatic symmetric function? It's just every way we can take some of these four stable sets in a way that does hit everything in every vertex in the graph at least once. We can do that by taking the 3 of size 1. We could do that by taking 2 of size 1 such that the other one is covered by red. We could also just take we could take everything. We could also take just the red and the green. And this ends up being the K-chromatic symmetric function in this expansion. So first nice thing is that this is quite nice, that the M basis just generalizes in a reasonable sense to some K-theoretic M basis expansion, and a finite one. It also has something of a deletion-contraction relation. It's a bit more complicated than for normal graphs because we now have that kappa of vertices can have intersection that is non-trivial. But essentially what happens here is that this is the graph without the edge UV. We have the classic deletion contraction components here, which is that we add the edge back and we contract the edge. And if we contract the edge, it will get a weight equal to the sum of the weights. And we do need, so when do we get this? That's when we're counting all colorings here where the colorings are exactly equal in the sense that they give the same exact set to both vertices, then that coloring is also a coloring here. If the two colorings have nothing in common, they are actually disjoint, then we could have added this edge back in. Unlike with the normal deletion contraction relation, we have other cases we have to consider. There's the possibility that kappa of u is a proper subset of kappa of v, and in that case, how we can end up counting that coloring is that we give that extra weight to u, but we also add edges from u to all neighbors of v, and that's what this is representing here. And this is going to work out because basically u has, say, colors 1 and 2, v has colors, say, 1, 2, and 3. And if that was the case here, then we instead give u the colors 1 and 2 here and give it the extra weight and give v only the color 3 here. But we still need these vertices to remember that they shouldn't be colored 1 or 2, which is why we need the edges to u. So the extra edge, so basically we are splitting these colorings apart so that we can have a proper coloring here. And the same thing here, if kappa of v is a proper subset of kappa of u, then we give extra weight to v, and anything that was in common between u and v now goes to only v. U gets the rest, and we draw edges from v to these neighbors so that those vertices remember some colors that they can't have. And the last non-trivial is when kappa of u and kappa of v intersect non-trivially in this manner, so that all of these portions of this Venn diagram are non-empty, in which case we actually just add a new vertex altogether with that weight. It gets the intersection as a color. U gets the kappa of u minus the intersection. V gets kappa of v minus the intersection. And again, this vertex has to remember what it should not be adjacent to, what it should be adjacent to. So a little bit complicated, but in the end it works. And the important thing that works here is that this actually does terminate. It's not immediately obvious that as a deletion contraction relation, this terminates because we're adding a vertex, but it turns out it does. You can show that the number of stable sets of size greater than 1 is strictly decreasing at each step. And ultimately that will decrease to 0. I see there's a hand raised in the
Hi.
Yeah.
I was wondering if you allowed for vertices to have no colorings. Would that simplify the deletion contraction relation?
Yeah, so it simplified it a lot because most of these cases don't happen. Actually, if you allow it to have no colorings, then I think you can basically just do 1 or 2 of these cases. I remember we talked about this.
So it could like go back to the original deletion contraction.
It would be more similar to the original deletion contraction. The downside of allowing our function to admit empty colorings is, well, the short answer is that Stanley considered a very similar function to ours, one which was, among other things, one of the things it did is exactly what you're suggesting, which is that it has 0 colorings. And so there, if you want to consider that, you could look at his paper. It's called something like Symmetric Functions and Related Colorings. It has a really long name that I can never remember. He made it because like the title, and the title has an acronym vaguely for Garcia Adriano, because it was some sort of special paper, and precisely because of that I can never remember the full title because it's like a really weird acrostic. But that paper has basically this function except where it allows weight 0 vertices. So if you wanted to look into that and see what's different about it and what's known, that would be a place to do that.
Okay, cool. Thanks.
Yeah, no problem. And I think somebody in the chat has possibly linked this paper. Yes, in that case, the deletion contraction relation is simpler. For various reasons, we wanted this to be our function, though, and mostly we wanted a way to compute it. And it turns out that this does terminate in the M-basis expansion, so we do have an efficient way to compute this function, at least, into some basis that we know. Now, we also want to talk about Schur and Grothendieck expansions of chromatic symmetric functions of both types. How this ends up working on graphs is, it especially matters for incomparability graphs. So a poset is a partially ordered set. It's some set of things, and it comes with a relation that is antisymmetric and transitive. The incomparability graph of a poset is the graph with the same vertex set, and distinct elements have an edge between them if and only if they are not comparable with respect to the poset. So here on the left is a perfectly good poset, and here on the right is its corresponding incomparability graph. So the incomparability graph of the natural numbers is the integers, as you can clearly see. But in any case, right, these two are comparable. A is less than B, and so they do not have an edge here. And on the other hand, A and E here are incomparable. All 3 of these vertices are pairwise incomparable, and so we get a clique for them over here. We also care about claw-free incomparability graphs. A graph is claw-free if there is no subgraph of it that is isomorphic to this, no induced subgraph that is isomorphic to this. The induced part is important. And why does this matter? Because we can say something quite nice about, this is normal chromatic symmetric functions of graphs. If G is a claw-free incomparability graph, then it turns out that the Schur function coefficient of this chromatic symmetric function actually is counting something very nice. It is counting fillings of the Young diagram of shape lambda with elements of the poset, and elements of the poset in such a way that we basically end up swapping the semi-standard conditions. The rows are chains in the poset. They are strictly increasing with respect to the poset left to right. and the columns are weakly decreasing going down in the or weakly increasing going down in the sense that no element in a column is directly above an element strictly less than it. So in particular, this graph has Schur-positive because it is a claw-free incomparability graph, and its coefficient of S221 its coefficient of S221 is going to be 4. Because these are the 4 ways we can fill a diagram of shape 221 with elements of the poset in a way that satisfies these conditions. So looking at this poset over here, for example, A is strictly less than B, D is strictly less than E, A and D are incomparable, D is less than C, that's fine, B and E are incomparable, that's perfectly fine. And you can check that each of these 4 satisfy it, and unless I miscounted, which is quite possible, I think these are the only 4 that satisfy this condition for this poset. So claw-free incomparability graphs are Schur-positive. One of our main results is that if G is a claw-free incomparability graph, then the K-chromatic symmetric function is Grothendieck positive. And as a matter of fact, it is somewhat similar in that the coefficient of the lambda Grothendieck function is a weighted sum over exactly those type of fillings for a certain Young tableau whose shape is either lambda or it's contained within lambda, in the sense of deleting boxes from rows and rearranging them to make it a partition. To briefly summarize the proof, because I do not want to go into too much detail, and some of this is not going to be stuff I've talked about in the talk, but we give a determinantal formula for the dual stable Grothendieck function, which I am notating using Oliver's notation as the S underbar lambda. And we use this known result to expand it in terms of homogeneous symmetric functions. And basically, we're kind of trying to mimic Gasharov's proof by lifting it to the K-theoretic setting. We apply the inner product with this function. We end up with something that is counting these colorings of these clique blowups of G. And Gasharov's result, as I gave you before, actually applies not only to a graph G, but also to its clique blowups. If you replace a vertex with a clique of size 3, you just use 3 instances of that poset element in the tableau. And so basically we're doing the same thing, except that whereas Gasharov started with expanding S lambda into H's, we have a lot more work to do by using a larger expansion, but ultimately the details work out. And this function is Grothendieck positive. So this I find is one of the compelling aspects of this function that really makes me believe that it is very nice and worth considering more, that it does lift this Schur-positivity result in a nice way. The obvious question to ask here is, can we get a topological interpretation then for these functions? One would like a subvariety of the Grassmannian such that these functions are induced for cohomology and induced for structure sheaf, respectively. In theory, such a thing should exist. In practice, I have no idea how to find it. And it's worth mentioning the Stanley-Stembridge conjecture, which is one of the big things that this has been coming from. This is why Gasharov believed and proved in the Schur-positivity, which is that it was conjectured that the chromatic symmetric function of those same graphs is E-positive. E-positivity is a stronger condition than S-positivity in general, since each E-basis element is S-positive, for example, by the fact that we could have applied the Gasharov theorem to cliques. So the obvious question to ask is, given that the Gasharov theorem lifts, might it be the case that the Stanley-Stembridge conjecture lifts? Is there some appropriate basis that is an analog of the E-basis in which our function might be positive? And the answer is no, not even close. We have tried, and it fails for a number of reasons. There seem to be 2 logical options for a multiplicative basis. We could start by defining that E in is going to be the Grothendieck 1 to the n and being multiplicative. We could also instead take it to be coming from the complete graph. Both of those two agree for usual symmetric functions, but they do not agree when they are lifted to K-theory. But it doesn't actually matter. Both of these obvious things fail. What ends up happening is that consider a 3-vertex path. So this is certainly a claw-free incomparability graph because it only has 3 vertices, and you can make the poset pretty easily. And what ends up happening is that this has an E21 in its chromatic symmetric function, its usual chromatic symmetric function. And it doesn't have an E3, I believe. So what's happening here is that you would need the K chromatic symmetric function is going to end up having an E bar 21. That's going to end up needing to be true regardless of which bar we're using. Now what's happening here though is the problem that if I'm using the graph E bar 21, then this is one thing I can do that is perfectly valid, is I'm getting this, it's an x1 squared, x2 squared. I could also do it with what ends up being equivalent to boxes, but I do have the same thing still. I could still have obtained an x1 squared, x2 squared. And the problem is that there's no coloring of this like this. Try to color this with 2 1s and 2 2s. Well, this certainly doesn't get the 1 and the 2. What if I tried to assign this the 1 and the 2? Well, then this still needs to be a 1 or a 2. It's not going to be a proper coloring. So we've come across an issue here. There's no actual coloring of this that outputs this monomial. So if we are going to end up being equal at the end, we're going to have to subtract some e at some point that cancels this excess monomial we've generated from lower term e's. This is a very straightforward and basic problem that we have here, that these things admit these monomials and this graph doesn't. And yeah, that's a problem. That strongly suggests that maybe topology is not the way to the Stanley-Stembridge conjecture. It certainly seems startling that the Schur-positivity lifted naturally, but E-positivity does not seem to have any possible natural way to lift. Some further directions. We did look for a little while at p-basis coefficients. Of course, the p-basis coefficients are infinite. We tried a couple of variants for a possible lift of the p-basis to a K-theoretic analog. Nothing we tried seemed to directly work, but there is enough nice things going on with the higher level coefficients that they seem to have combinatorial meaning in a way that I'm not 100% sure we figured out. And a reasonable question to ask is, do there exist graphs with equal K chromatic symmetric function? There certainly exist graphs with equal normal chromatic symmetric function. The smallest example being these. But these do have non-equal K chromatic symmetric function. And it's actually not hard to see this either. One thing you can look at is what is the size of the largest size of a stable set that contains a given vertex. This vertex is not in a stable set with anything else, which in particular means that if you cover this graph with stable sets, you must include this. You must include a part of size 1 for the M basis. There is no vertex over here that has this property, that every vertex over here has non-trivial stable sets that it's a part of. And so there are terms over here that do not have a part of size 1, whereas every term over here has an M lambda with a part of size 1. And so these are not equal. And as a matter of fact, in our admittedly somewhat limited time looking at this particular question, we have not actually been able to find graphs that even make it past this basic hump. I'm sure that there must be graphs that make it past this basic hump, but I still wouldn't know if they would have equal K chromatic symmetric function. It's an open question whether trees are distinguished by the normal chromatic symmetric function. It might be nice to use this as a starting point. That's something that would hopefully be weaker and easier to prove. Yes, I see hand raised again.
Hi. Is it true that the never mind. I was gonna ask if the K-theoretic symmetric chromatic function if the chromatic symmetric function distinguishes, then so does the K chromatic, but that's like clearly true.
Yes, it's true
Yeah.
because the lowest degree terms of the K-chromatic is the normal chromatic. And that is my talk. Thank you so much for listening.
Thanks so much for a very nice talk. Let's thank the speaker.